Hello viewers. In this video let's discuss about the principle or theory of size exclusion chromatography. To understand the principle behind the molecular separation according to their sizes, we said this chromatographic technique is discriminating the analyte components according to their sizes. So let's choose an ideal mixture of two components. Just imagine that I have taken two components here. It is like injecting the sample. It has been injected into the port, and then we'll allow the mobile phase to pass in. So imagine that this is a mobile phase which is passing in. Now as the mobile phase starts to pass, it is just passing through the column at a fixed rate, and as the mobile phase pass, this will create a pressure gradient. So as this pressure gradient is created across the whole length of the column, slowly the sample polymer molecules pass into the column as a result of this pressure gradient. Now we can see that there is a stationary phase. All this column, throughout the length of the column, it is packed with a stationary phase. This contains a porous material, and all this porous material, it will have a controlled pore sizes. All this porous material come with a range of pore sizes as we have discussed in the last video. Along with these pore sizes, there are also some interstitial spaces. So within the stationary phase, we must remember that altogether there are two spaces. One is a space within the particle, we call it as a pore, and the another one is a interstitial space. So one is within the particle and the another space is in between the particles. So whatever analyte components, whatever macromolecules that are to be separated, they can settle either into the pores of the particle, or they may settle into the interstitial spaces between the particles. Right. Now for an ideal mixture, as we said, we have chosen two component mixture. One is of a larger size and another one is of a smaller size. If I am choosing a smaller macromolecule, that smaller macromolecule, it can slowly penetrate as it is passing through the column. It can slowly penetrate into the pores of the porous material, because they are very much smaller. So as they are passing through the column, slowly they try to enter into the particle core, and then they will settle into the spaces. Whereas the larger ones, they just cannot enter into the pores of these particles, therefore they will try to settle into the interstitial spaces that are present. So as the column is running, we can see. So just put it, let me put it here. Imagine that these are the larger sized macromolecules which are unable to settle into the pores of the stationary phase packing, whereas the smaller one, they are able to settle into the pores. Now slowly a separation can be seen. So as time passes by, these larger particles will come through the interstitial spaces. They are just coming out of the column, and these are separated from the smaller sized macromolecules. So this will produce a peak for the larger sized molecule, and as the elution continue, these have completely come out. Now a smaller sized particle is coming out, so that will produce another chromatographic peak. Right. So this is how we have seen the separation. So smaller molecules, what exactly happening is, these are retained into the pores of the particles, and this retaining is only temporary. They just start to flow down the column when they encounter other particle pores to enter. So suppose if I am choosing two different particles, particles of the stationary phase 1 and 2, and the smaller macromolecules have settled in one of the particles of the stationary phase, slowly they can come into the interstitial spaces, and then again they can go and settle into the pores of the other particle of the stationary phase. This will take some time. Whereas the larger particles, they just cannot enter into the pores of the stationary phase particle, therefore they directly settle into the interstitial spaces. So this will give them a lesser time to spend within the column, and as it is spending a lesser time within the column, they are coming out first. So the first elution is of the larger macromolecule, and the next solution is of the smaller macromolecule. So this is how the larger molecules are being separated from the smaller one. The larger one, they are flowing more rapidly through the column, as we said, because they are unable to reside into the pores for whatever may be the given period of time. So just let us discuss about a little thermodynamics, not getting into much details, but suppose if I am choosing one particular particle, let me enlarge it. This is only one particle, but I am taking 4 different pictures of it. There will be like a mesh in it. All these can come as beads, micro beads, and these are creating some pores within it. So our ideal mixture has only 2 components now, and supposing that this is the pore, let me choose the 2 particles. One is of a larger size, so the larger one I am still making it larger. Now if it is very large, just imagine that it is so large it is unable to settle into the pores of this particle of a stationary phase. Since it is unable to settle into these pores, slowly it is coming out and it is settling into the interstitial space. So again, when it encounters another particle, again it cannot enter into the pores, so it is again coming out of the it is not entering into the pores, and it is coming through the interstitial spaces, and finally it will flow through the column and it will be eluted first. But suppose if I am choosing a smaller particle, that smaller particle can very easily settle into these pores. So since it is able to settle very easily, it will take a longer time and it will spend more time in the column. So it may come very slowly into the interstitial space. As it encounters another particle of the stationary phase, it will go and settle into it, and again it will come into the interstitial space, and this process will continue, which makes a much longer retention time for this. For much information, just let me take this particular portion. I am still enlarging it. Suppose if this is that position. Now let us assume that there is also another macromolecule, but its size is intermediate. Previously we have taken only 2 size macromolecules. One is of a very large size, which is unable to settle into the pores of the particles of stationary phase. Another is of a smaller size, which can very easily enter into the pores of the spaces of this particle of the stationary phase. So let me take an intermediate one. Suppose that if I am taking an intermediate one, let its size be this one. So it is able to settle into the pore. It is able to settle into the pore, but we can see if we can just count this, there are about 9 pores in this. So within these 9 pores, if the particle is very small, just imagine that 9 particles are being settled into this. But due to the intermediate size of this, only one particle is able to settle in this pore size. There is only one particle, right? I am just making it into a grid in the sense, just break it into 4 portions. So this smaller portion, I am just enlarging it. I am taking an intermediate macromolecule size. That intermediate macromolecule could settle into the pore of the stationary phase particle. Only one particle is allowed at a time. If I compare this with a smaller one, now that smaller one is also settling into the same space, but if I break it into grid, now that can settle here. That smaller particle can settle in this portion, or second position, or third position, or it can also settle into the 4th position. So it simply means that the smaller molecule has 4 times as many possibilities for the retention as the larger molecule. So since it has more number of positions which can be occupied, we simply say that its entropy is higher. So whenever we say entropy is higher, it is enjoying a greater freedom. In comparison to a larger macromolecule, a smaller macromolecule is enjoying a greater freedom. Hence its entropy is high, therefore it is not ready to come out of the pores of the particles of stationary phase. Whereas intermediate or a larger particle which has a lesser freedom relatively, So since it has a lesser freedom or a lesser entropy, it is not taking much time into the pores of the stationary phase particle. Therefore it is just coming out of it. It is staying in the interstitial spaces, and as when it stays in the interstitial spaces, whatever mobile phase that is coming out, it will wash away these solute particles and it will elute it in a very smaller time. So this is the principle or the theory hidden behind it. And also one more important point that I'll tell you. If at all we take the thermodynamics of a regular gas chromatography or a liquid chromatography, in the case of liquid chromatography, what is the basis for the separation? Means it is based on partitioning, or it is based on adsorption or ion exchange method. So all these partitioning or adsorption or ion exchange methods, they involve intermolecular forces. So we can witness the intermolecular forces between the solute and the stationary phase. So whenever there are intermolecular forces, we say that enthalpy will play a major role, and the interaction between the solute and the stationary phase is found to be exothermic. So as it is found to be exothermic, the equilibrium constant in such a case will be greater than unity. So if it is a regular LC, the equilibrium constant will be greater than unity, and whenever the equilibrium constant is greater than unity, the solute peaks will elute after the solvent front. All this come under the basics of chromatography, which is not our topic of discussion. It will be discussed in a separate class. But when it comes to the case of the size exclusion chromatography, the regular the topic of our discussion, the solute distribution between the two phases, we can see that the solute distribution between the two phases, it is totally controlled by entropy. There are no intermolecular forces between them, therefore enthalpy become negligible. Entropy will play a major role, and there are no such interactions like adsorption or ion exchange or partitioning. So as there are no such interactions, enthalpy is decreasing. But since these particles are going and settling into the pores, it is just leading to a greater freedom, and therefore entropy become more important. So as entropy become more important, and as it has to come out of these spaces, as it is coming out of the spaces, its entropy will be dropped, and this decrease in the entropy will make the equilibrium constant lesser than unity. So because it is just enjoying a greater freedom, all that greater freedom which is enjoyed by these particles is suddenly lost as it is coming out of the column, and therefore we say that there is a decrease in the entropy, and whenever there is a decrease in the entropy, the equilibrium constant is found to be lesser than unity. So this is in the case of size exclusion chromatography, whereas this is in the case of a regular liquid chromatography. So in the case of size exclusion chromatography, solute will elute before solvent front. But in the case of liquid chromatography, we have seen that the solute particles or the solute peaks will elute after the solvent front. So this is the principle and the theory hidden behind the size exclusion chromatography. So just to conclude, suppose if we are choosing